Good morning. Today I'm going to teach application of Fourier series. Using Fourier series, we can solve one-dimensional heat equation, wave equation, and many more partial differential equations. So, Fourier series is used to solve partial differential equations. Now, the first is one-dimensional heat equation. Consider a thin homogeneous bar or a wire of length L. So this is a wire or bar of length L along x-axis. Let u function of x and t, where x is displacement and t is the time. Let u denote the temperature distribution or heat flow within this bar. Under the condition that at the ends of the bar the temperature is 0, means u 0 comma t is 0, u L comma t is 0. So the heat equation is given by this. It is the partial derivative of u with respect to t is equal to c square second order partial derivative of u with respect to x, where x is lying between 0 and L and time is greater than equals to 0. Here it is equal to 0 with the initial conditions. Initial boundary conditions are that at end points the temperature is the temperature is 0. So u0t is equal to ul is equal to 0. With initial condition that at t is equal to 0 the temperature is some function of x. So under these conditions we have to solve this one-dimensional heat equation using Fourier series. So first of all we assume that uxt, which is nothing but the temperature, it is the product of distance function and time function. This we choose by the method of separation of variation, that we assume that solution is of this form. It's a product of function of x as well as function of t. Now since this is a solution, so clearly it satisfies equation number 1. So we have to find its partial derivative with respect to t. What is the partial derivative of this equation with respect to t? It will be curly u upon curly t. It is independent of t, so this is as it is, x function of x into the derivative of this function. This is t dash t. So we get this thing. So the partial derivative of u with respect to t will be this much. Similarly, for the right hand side, we have to find the second order partial derivative of u with respect to x. So we first find out the first derivative u with respect to x. From here, since it is independent of x, so we take the derivative of this with respect to x. So this is x dash x t as it is. Similarly, we find out the second order derivative. Now we substitute the value of this and this in equation 1. So what we get, xx t dash t is equal to c square x double derivative of a with respect to x into t. Now separate the variables. Separate the t variables as well as x variables. Since two ratios are same and both are the functions of different variable, this is function of t only, this is function of x only, and these ratios are same. This is possible only when these ratios are equal to some constant, say it is lambda. Okay, so one time we substitute this equal to lambda, one time we substitute this equal to lambda, and solve these ordinary differential equation. This is first order ordinary differential equation, this is second order ordinary differential equation. So now we have to solve these two differential equations separately under the different values of lambda, right? There are different cases that lambda is 0, lambda is greater than 0, and lambda is less than 0. For these three possibilities, we will solve these differential equations, right? Now, what are the boundary conditions under this solution? What are the boundary conditions? That at end points, the temperature is 0. So now you just substitute x to be 0 here. So you will get u 0 comma t is equal to x at 0 into t as it is equal to 0. Right? So from here what we get? Since time cannot be 0, this equation is hold for all t. Okay? So always time is not 0, so we will get this should be 0. So we get x at 0 is 0. Similarly, ULT 0 implies x at L it is 0. Okay, so our boundary conditions reduces to this much, that x at 0 is 0 and xl at 0 is x at L is 0. So now these are our boundary conditions now, and now we have to choose different values of lambda and we have to solve these differential equations. Okay, for lambda 0 and lambda greater than 0, we will get trivial solution. How? We will do later on. Now first consider lambda is negative. Say it is minus k square, where k is any real number. Then we have to substitute the value of lambda in two equations. The first equation is x double prime x plus k square xx is 0. Right? This is second order differential equation with constant coefficient. So we assume e to the power mx be a solution. We get auxiliary equation m square plus k square equal to 0. Solve this, we get m is equal to plus minus k iota. Since it is imaginary roots, so the solution will be of the form e to the power real part is 0 here. So the solution will be c1 cos kx plus some constant times sine kx. This is the general solution of this differential, second order differential equation. Now we have to apply the conditions, boundary conditions. X at 0 is 0 and x at L is 0. So when you take x to be 0 over here, what we get? We get c1 cos 0 is 1 plus c2 sin 0 is 0. So we get c1 cos 0 which is 1 equals to 0, means c1 is 0. Now substitute x to be L. So we get the equation c1 cos kl plus c2 sin kl equals to 0. But c1 is 0. So we get c2 sin kl is 0. Now just see, there are two possibilities, either c2 is 0 or sin kl is 0. But if c2 is 0, c1 is also 0. So we will get only 0 plus 0, that is trivial solution. If this is 0, then the main solution uxt, which is product of x and t, this is 0, so that will be also 0. So we will get the trivial solution, but we are interested to find out non-trivial solution, so we discard this case that C2 cannot be 0. So this implies sin KL should be 0. Now sin KL is 0 for sin n pi, where n is varying from plus minus 1, plus minus 2 and so on. So we get the value of k, which is nothing but n pi by L. So now substitute the value of C1, C2 and K over here. So we get xx is equal to C1 is 0, C2 is as it is, sine k n pi x by L. Since our k is depending on L, so we consider x to be as a function of L, n, right? So x1 will be some constant times sine pi x by L, x2 will be some constant times sine 2 pi x by L, x3 will be some constant times sine 3 pi x by L. So I replaced x with xnx because it depends on n, replace the constant with cn because it depends on n, into sine n pi x by L. Okay. Similarly, solve this differential equation. Substitute the value of lambda over here. It is minus k square, right? This is first order differential equation, linear differential equation. We can separate the variables over here and we can solve it. So we get this is some constant times e to the power minus c square k square t. Again we can substitute the value of k. K is what? It is n pi by L. So again it is depending on n. So we write Tt as Tnt because it depends on n is equal to some constant which depends on n, e to the power minus c square n square pi square t upon L square, where n varying from plus minus 1 plus minus 2 and so on. Okay, so we'll get the value of xn, we get the value of Tn. So our solution is also depending on n, that is unxt, which will be the product of these two, right? But we know that whenever y1, y2, y3, these are the solutions of some differential equation, then their linear combination means c1y1 plus c2y2 plus c3y3 and so on, that is also a solution. So since u1xt, u2xt, u3xt all are the solutions, so therefore their summation is also a solution. So uxt will become the summation of unxt, right? Where unxt is xnx into tnt. Now substitute the value of xn and tn. Our Tn is Bn e to the power minus e square n square pi square t by L square, and Xn is Cn sin n pi x by L. So we can combine these two constants. So replace Bn into Cn with some another constant Dn. So this is a solution of differential equation. But now we need to find out the value of Dn under the initial condition. Initial condition is what? Ux at 0 is some fx, where x is 0 to L. Here it is not boundary condition, it is initial condition. Boundary conditions are that at the end points the temperature is 0. Now when T is 0, Ux is fx. So take t to be 0 over here, you will get ux0 is equal to summation n varying from 1 to infinity dn e to the power 0 is 1 sine n pi x by L. So, and ux0 is what? It is fx, so you can write ux0 to be fx. So we will get this series. This is clearly a sine series, right? Also, this is half range Fourier sine series. Now, why it is half range Fourier sine series? Because from here we know that it will be sine n pi x by half of the period. So here it is L. So period of this will be 2L. But our series is defined on the interval 0 to L. So that means half range is given to us. So this is half range Fourier sine series, and we know that how to solve half range Fourier sine series means we can find out the value of dn. It will be 2 by L 0 to L fx sine n pi x by L. So now we have to solve this integral and find out the value of dn. After getting the value of dn, we will substitute this in equation number 2 and we will get the complete solution of this one-dimensional heat equation. So we will get the solution of this differential equation using Fourier series. So we will find out the value of coefficient using Fourier series. For example, find the solution of heat equation where x is lying between 0 and pi under the boundary conditions at end point temperature is 0 and the initial condition at t is equal to 0 ux is sine 3x. We have to solve this differential equation under these conditions, right? So the solution is given by uxt is summation dn e to the power minus c square n square pi square t upon L square. L is pi here. So substitute over here, we will get this is cancel out into sine n pi x by L. Here pi L is pi, so this is also cancel out. So we will get this is dn e to the power minus c square n square t into sine nx. With initial condition at t equal to 0, ux0 is sine 3x. So substitute x to be 0, we will get the value of this to be 1. So this is half range Fourier sine series on the interval 0 to pi where dn is 2 over pi integration of sine 3x into sine nx from 0 to pi. One way you solve this integral, the other way we can compare the both sides. Here it is sine 3x is equal to d1 sine x plus d2 sine 2x plus d3 sine 3x and so on. So after comparing we get d1 is 0, d2 is 0, but d3 is 1, d4 is 0 and so on. So we will get the only value of d3 which is 1. Now substitute this value in this solution. So uxt is equal to d3 is 1, all others are 0. So substitute the value of d3 which is 1 e to the power minus c square 3 square t into sine 3x. So this is the solution of this partial order differential equation. Okay. Now here it is given that why we discard the cases lambda is equal to 0 and lambda greater than 0. Now just see, when your lambda is 0, equation will become t dash t is equal to 0 and x double prime x is equal to 0. Its solution is constant. It is this one. Under these conditions we will get C20, C30. So we will get only trivial solution. Same way, when we choose lambda greater than 0, again we are having the trivial solution only. So that's why we discard this case and we always consider lambda to be negative, because only in that case we will have non-trivial solution. So no need to do this, just write down that for lambda equals to 0, lambda greater than 0, we will get trivial solution. So we take lambda to be negative, and in case of lambda negative we have this solution. So under these initial conditions, just simplify this solution, find out the value of the coefficients and substitute over here, we'll get the final solution. Okay, similarly we can solve wave equation using Fourier series under some conditions. Now wave equation is modeled by the equation curly square u upon curly t square is equal to c square curly square u upon curly x square. So here we have both second order partial derivative with respect to t and with respect to x. And we have to solve this differential equation under the boundary conditions that at end point temperature, here it is wave, so at the end point this u is 0, with the initial condition that when time is 0 u is fx and its derivative is gx. Again solve these differential equation using the same way as in heat equation, as done in heat equation. Okay, so after solving this, for lambda negative we will have this as a solution, that is uxt is the summation n varying from 1 to infinity an cos n pi c t by l plus bn sin n pi c t by l times sin n pi x by l, the same way as we have done in heat equation. First we assume that uxt is nothing but the product of two x function as well as t. Then under these conditions, boundary condition, find out the new conditions. Then solve two second order differential equations. We will get this thing for lambda negative. Okay. So now the first condition is u, x at and t at 0. Its value is fx. So when you take t to be 0, this is 1. This is 0. So we'll have an into sine n pi x by l. Again, this is half range Fourier sine series. We can find out the value of this coefficient, and its formula is 2 by L integration 0 to L fx sine n pi x by L. Solve this integration, find out the value of an, and then you can substitute over here. But we need to find the value of bn also. So we use this condition. Take its derivative with respect to t to both sides. Okay. Now find out its value at t is equal to 0. This will be gx. So at t is equal to 0, now this time this value is 0. This is 1. So we will have bn n pi c by l into sine n pi x by l. Again this is half range Fourier sine series on the interval 0 to L. So we can find out the value of coefficient. Now in this case, Bn is not only coefficient, but Bn into n pi c by L. This is the coefficient. So we'll get the value of this. It is 2 by L integration of gx into sin n pi x by L from 0 to L. Solve this value and find out the value of Bn by taking this number to the right side. You will get the value of Bn. Okay, so from the first case we get the value of An, from the second case we get the value of Bn. Now substitute the value of An and Bn in equation number 1. We will get the complete solution. So in this way we will solve wave equation. For example, let an elastic string of length L, which is fastened at the ends at 0 and L, picked up at center L is equal to L by 2 to a height of L by 2 and released from rest. So we have to find the displacement of string at any instant of time. That means we have to find uxt. Here uxt denotes the displacement, x denotes the distance, t denotes the time. So these are the boundary conditions, that at 0 and at x is equal to L, the displacement is 0. And x0 is fx. That means, now just see from here, it is saying that at the center point x is equal to L by 2, it picked to a height of L2. So the function is of this form. It will be x along this side. From when your x is varying from 0 to L by 2, and here the value of fx is L minus x. Whenever your L by 2 is your x is varying from L by 2 to L. So now clearly, when you take x to be 0, this is 0. When you take x to be L, L minus L, this is 0. So at end points, this value is 0. So this is the function. So at t is equal to 0, our ux is fx, which is this one. And at midpoint, at x is equal to L by 2, this is L by 2, L by 2. And released from rest means the derivative is 0. Its velocity, initial velocity is 0. At t is equal to is 0. So these are the conditions. Under these conditions, we have to solve wave equation, which is given by curly square u upon curly t square equals to c square curly square u upon curly x square. And we know that the solution is given by this. Now just see, I have only cos term, not sine term, because this is 0. So that value is always 0. Right? And this is at t is equal to 0. This is nothing but Fourier sine series. Half range Fourier sine series. When you put t equal to 0, this value is 1 and uxt is fx. So we can solve that half range Fourier sine series. That means we can find out the value of dn, which is given by this formula. This integration will be split into 2 from 0 to L by 2 and L by 2 to L. In case of 0 to L by 2, substitute fx to be x, and L by 2 to L, substitute L minus x. After solving, we will get the value of dn to be this one, which will be 0 for n even, and for n odd the value is this much. So now you substitute the value of dn in this equation. So we will get the complete solution. Thanks.